All right, good morning, everybody. Thank you for being here today. I'm excited to go over basic ultrasound system maintenance, backup procedures, and probe testing essentials. Do we have any veterans in the group at all? Happy Veterans Day to all of those that are here today. Like I said, my name's Tom. I've been working in the ultrasound service and management for over 16 years. I started off as a field service technician and now serve as a senior service director at MW Imaging. So I've seen both the technical side and the leadership side of this field. Before I worked at MW Imaging, I worked at a local facility in the St. Louis area as a Biomed 1 through 3. Also served in the U.S. Army for 8 years as a 91 Alpha MOS out of Shepherd Air Force Base, Wichita Falls, Texas. Does anybody have, anybody currently here work with ultrasound systems or service any ultrasounds at their facilities? What type of systems are you guys working with over there? GE and Mindray, okay. So we're gonna cover some, and Philips systems. We're gonna cover backup procedures for GE systems and both Philips systems, how to create a backup, show you where you find IP information. Go to the next slide here. That's me, nice picture. All right, so overview of the class today, things that we're gonna cover. First, go over how ultrasound is produced, how to create a system backup for GE systems, cover where to find the IP address and wireless network information. Same thing for Philips systems, where to back it up at, and then we're gonna go over a general quality assurance testing for ultrasound transducers. All right, how is ultrasound produced? One of the core components to ultrasound is the transducer. Inside the transducer, you have 256 crystals, piezoelectric crystals that convert electrical energy into mechanical sound energy, and vice versa, sound energy back into electrical energy. In order to do this, you have to have a pulse to the crystal. The system sends electrical pulses to the transducer. These pulses are generated by a circuit called the pulsar circuit or a transmit board inside the ultrasound system. Once it generates this pulse, it vibrates the crystal and generates sound waves that travel through the body. Once the sound waves travel through the body and hit and deflect off of organs or tissues, they reflect back. We call this reflection back echo receptions. Different tissues reflect different amount of sound based off of density and composition. When this electronic sound echo comes back and hits the piezoelectric, comes back to the ultrasound probe again, and then hits the piezoelectric crystals and converts these mechanical echoes back into electronic signals again. These electronic signals are then processed, what we call a process called signal processing. They go through the ultrasound system and hit the beamformer, which amplifies the signals, filters out the noise, measures timing, and determines signal strength. Once this signal is processed, it then goes to image reconstruction. The scan converter translates timing and amplitude data to form your 2D grayscale image. The brightness is represented by the strength of echoes that are reflected back to the crystal. Finally, you have the image displayed in real time on the system monitor, allowing users to observe anatomy, movement, heartbeat, and flow. Do we have any questions on how ultrasound is produced? It's just a basic rundown. Importance on ultrasound systems backups. A lot of times when I get calls for tech support, whether the system has an error code or it's down or it don't sorry. Once the system is down or is given an error code, one of the first things I ask for is if there's a good backup of the system. And that was for recovery purposes. Some of the importance is to make sure you're preserving configuration and presets. Make sure the all ultrasound systems are customized with site-specific presets, measurements, and workflow preferences. Backups ensure that these settings can be quickly restored if the system crashes or undergoes repair or requires some type of software reload. Like I said, when I get calls for tech support, that's one of the first things I ask if the system has a backup. A lot of times when you go out on service call, you'll find that the backup could be 2 to 3 years old. So if any changes have been made to the system between that time, they won't be recorded, obviously. Some of the things, this supports preventive maintenance. Part of what I make sure our techs do is every time we're doing a PM on the system, I want them going in and making sure that the first thing they do is create a backup, prevents, like I said, data from being erased, assures that critical information is recoverable, restores system configuration and presets, supports troubleshooting, and helps minimize our downtime if we're going to do a repair, or if we have to reload system software, or the hard drives are having an issue. We want to make sure we can get the system back up as quickly as possible. Three keys to a system backup that I always make sure to ask the customers is, one, do they have license options of the system? In order to recover the system, you want to make sure you have these purchase features. Each one of them is unique to your system. Without it, a reload of system software or bringing the system up to being usable wouldn't be possible if you don't have the license options of the system. Typically for Philips systems, or the newer Philips systems, if you create a backup, it will save the license options file. Older systems like IU-22s and IE-33 ultrasound systems, they didn't record or back up the license options. So it's always important to make sure that you have a copy of your license options. For the GE systems, the option is like a window string. Instead of a string of characters or numeric symbols or, on the system. The second thing, after you make sure that they have the license option settings, you want to make sure that they have the user settings. These settings are user-defined presets, measurements, workflows, annotations, DICOM settings, and network configuration. And the third thing you want to make sure that they have is the system IP address, or know that the network that they're on, or if it's wireless, wired, whether it's a static or a DHCP type network IP address. So these are the three keys to the system backup that I always make sure that that are recorded. We typically record these in our service management system software. Anytime we're performing a PM, we make sure that we've got these three keys backed up, and then that we, like I said, that we record them in our system management software. Getting started with backing up Philips and GE machines. Typically, you would arrive on a site. If you need to make a backup, power on the system, you go into support or utility. For GE systems, you would go to the system tab, select backup restore. Make sure you use some type of backup media. Typically, all the newer systems use USB devices. Some older ones use CD-ROMs. I can go over through here. All right. So I'm going to go through and show you the menu settings on how you would back up a GE ultrasound system. This particular system here is a GE Logic E system. When you're backing this particular one up, you want to make sure you have the USB plugged in, the thumb drive plugged in. For this one, you would go to utility. All right, come up with a menu like this. Typically on all of them, you'd see backup and restore setting here. All right. For GE systems, you would do user-defined configuration and service. Make sure you select your drop down from the media here, and then you would hit backup. Now for most GE systems, they're going to come up with a little warning, backup user-defined configurations, and it tells you where it's going to. You'd hit OK, and it should continue on with the backup. That one said user-defined. This one says here service, backing up the service settings folders. OK, and then for GE ultrasound systems, most of the time when you've created your backup, you should see over here on the right-hand side, it was finished. It should give you the time and date stamped, and that's how you know if it was backed up successfully. Once you have the user-defined configurations backed up and the service backed up, you want to make sure that you go to check on your wireless or network configurations. And for GE systems, that's done under connectivity. And here, if it was plugged into if it was plugged in hardwired, it would give you an IP address here, tell you the network speed, and give you the MAC address. Same thing for wireless configurations. If it was on the wireless network here, if you needed to go to configure it on a wireless system, you would go to this page here, and it would bring up your wireless networks. You could set up your properties and security types over here on wireless. Anybody have any questions on how to back up ultrasound system GE? So after I create a backup for these systems, typically on the USB, I think it's very important that we indicate a couple things on the USB device. Usually I use like a little white sticky on there. I'll make sure that I record the time and date that I created this backup. One other thing I want to make sure is I have is the R level of the system software level, which you can find under the About System tab and the About tab. So typically, if there's ever an issue with GE systems, one of the first things that they would ask you is what R level is the system here, and you can find that over here under the system image type number R9.1.2, and this is the software revision level for the particular system that you have. So if for some reason that it was just bricked up and you tried to power it on and you would get nothing, maybe just a GE logo or an error code, and you couldn't get to this page, sometimes the backup can help you with that if it's labeled properly. So I like to label all my backups with the time and date, what R level is, and what R level of the system it is, as well as the system serial number. General. So we covered how to create a backup, service backup, and user-defined presets. We covered where to find the TCP/IP information. The last thing I want to go over is where you find the license options. So that was the third key that we were talking about. And you would do that on a GE system under admin in the system admin tab here, and then you can see here where it has the installed options key right there. Without this key, if you were to go to reload system software, you wouldn't be able to get it running again. It wouldn't function the way you want it to. One of the important parts that you want to know here is the hardware number here. Typically when we record these, we typically take a picture of this, and I would upload this picture to my system management software, or I would just simply write in or record the details that I see here in system management software. But I would make sure that I had the system serial number, the hardware number, and the installed options key. Any questions? Yes, sir. Yeah, for there, Some of the systems, like the Volusen systems, it asks you to eject them before you remove the device. So there is a spot on here. Yes, so on a CD, if you were to try to pull out a disk, it does give you several options when you go to eject it, and it would say, verify and deal. Most of the time, I'm using USBs, so I don't really have to worry about that. But when you're using a disk, yeah, for like the Volusen systems or stuff like that, and GE Logics, yeah, when you did it, it will give you an option with a CD-ROM device to verify that it was written to that when you hit eject there. So here it gives you an eject. Most of the systems for GE systems give you an eject button, and that's what he's talking about. When you hit CD DVD recordable, it will come up here, verify or whatnot. So. All right. Cancel. All right. So that covers our GE systems. Continued. Okay. All right, since we covered that system, let's go back over to here. Moving through. All right, so this one's a Philips ultrasound system. Same type of concept, but backing it up. I'll move this over here. So on each one of these control panels on a Philips system, on the newer ones, they have a support button. It's on the top right-hand of most of the control panels on here. This is a Philips 5500 system here. It's one of their newest portable systems that they have out. All right, so under here under system management, we were talking about labeling software versions and levels. Here under this system management tab, system identification, all right, right here in the software version, it will give you, when you're labeling your drive, this one is software version 1.0.2, all right, your system serial number, all right, and the cart or hardware version for Philips systems. On the left-hand side here, backup restore, all right. I typically use thumb drives when I'm, like I said, when I'm backing up. Come over here, select the drive. And then back up. Now this will go on the Philips system here. It gives you a list of the things that it's backing up here. And we were talking about the 3 keys that we wanted to make sure that we had backed up. One of them obviously was the options here. If you go through this list here, I think it says clinical options here, right here. Clinical options were queried and copied successfully. So that's one of the things that you want to make sure. And then as you scroll through here, you can see all the different files that were backed up here. At the bottom of here, it says here the system settings were successfully backed up to media device. You can see that your DICOM settings were backed up here. Printer settings are backed up. TCP IP settings were backed up. But still, even though that they're saying most of them are backed up on the Philips ultrasound systems, I still make sure that I go and copy the IP address. So I'll go back in here. When you're doing a software recovery or reload on any of these systems, typically it doesn't save the system IP address of the particular ultrasound system. Now it will restore your DICOM servers, workless servers and stuff like that, but it won't. It very rarely do I see that it records the actual IP address of the system when you're doing a recovery. So under network settings here, wired information. So if you're doing wired or wireless, you would have to select from the drop down over here on the right side. If you had wireless settings or wired settings. And then over here on the right here is TCP IP properties. You would click on that and it would tell you whether it was obtained automatically, it was DHCP, or it was set to static. So I would always make sure that I copied these again in our service management system software, so I know what the IP address is if I had to recover it if the system was completely down. So we covered IP address, one of the keys. We covered license options, which is another key. And user-defined settings were all covered in our backup restore. Now, a couple things just to go over and cover it on the Philips side of the systems. If the system was up and running, but it was still giving you some type of issues, you can come over here and run a system confidence test on here. I think it's like a 8 or 9 minute system test here. It runs the same diagnostic tests as if you were to, log into the system, or Philips was there to look at it. But typically, program in probe, show you what it looks like. Yeah, this one haven't failed. Now, the system was shipped to me today and it kind of broke the side of it, so as it came in today, so I got a little bit of an issue with it, but yeah. But if you had an issue with the system, it would do just like this. You run the test, you get a fail, you could export this log too as well. See, it gives you a button down here to export the logs. All right, same thing, export it to the USB device. All right, you can send it into Philips tech support, whatnot. They can take a look at it and see if they can figure out what's going on with it. They should be able to give you an answer on what's going on. Files were successfully sent to the system. All right. All right. One other thing I wanted to go over here too is there's another export here that you can do that you can send to the USB device, is export all the logs to the system here. So it's under system management, log management. You can come over here and export logs as well. Typically, they'd want you to include all the logs in order to send them over. Now, this could take quite a bit of time to go through the logs to send them over there. Any questions on how to back up a Philips ultrasound system? Here. Over to the other device here. So with manually. So we're going over Philips systems, downloading error logs. All right. All right. Is anybody familiar with the ultrasound phantom at all? All right. So this is our ultrasound phantom that we use. On here you have wire dots that are all measured on here. This particular one tells you whether it's 10 millimeters or 1 centimeter difference. You also have these anechoic structures that you can hit here on the right hand side, and then you have a grayscale as well on this particular phantom. So when you're running through and doing a quality assurance for ultrasound transducers, when we do RPMs, when when our field service technicians go and do a PMs, we're doing tests for each one of our transducers. A good ultra quality assurance program is a routine testing and checking and verifying that the ultrasound probe and transducer is performing correctly, safely, and consistently according to clinical and manufacturer standards. The tests that we run through are, the first one we do is what we call an air scan. We would put the transducer, hook it up to the system, and basically just scan air with it and see what the array looks like. The next one we would do is a depth of penetration test. Then we do a functional test of it. And then we do a geometric accuracy test, a beam profile test, axial and lateral resolution test, grayscale test, and a color noise or cable test. Or some of the tests we do for quality assurance testing on our probes. The importance of quality assurance is one, this process of routinely checking and verifying that an ultrasound probe is performing correctly, safely, and consistently. Obviously, the biggest thing is patient safety. A damaged probe may produce excessive heat, electrical leakage, or inaccurate images that could harm the patient. Diagnostic accuracy, poor probe performance can lead to misdiagnosis. Consistency and reliability. A routine QA testing ensures images are consistent over time and between different transducers. And cost savings. Early detection of probe issues can prevent expensive system damage or repeat exams. Early detection of probe issues may allow for repair rather than replacement of the transducers. This here. So we're going to go through some of the tests that I typically do or my techs do for PMs on transducers. Typically when you go in and do a PM, there's could be one transducer on the system, there could be 8 transducers on the system. We have a PM form that breaks down all of these tests, and we indicate our distance measurements between them and each transducer. We're at here. Go over here. All right. So this is on the top here. We got this particular 12L, 12 linear probe on this system. It's frozen right now. When we talk about an air scan, this is typically what it looks like on the system here. We got uniformity across the top of the array here. You see there's no dropout, no elements missing on this particular transducer. I would give it a little wiggle here at the top here. Make sure that I don't see any issues with the transducer. The first test we typically do on here is a depth of penetration test. And for the depth of penetration test, I put it on the Phantom here. All right. One thing you want to make sure that you're doing here is that when you're going to, you want to keep your, so I record all of them. So the first thing I'll do is I'll create a patient. All right. Typically I would call it test study. All right. Or test PM. Typically if I'm doing a PM, I'll put on here the date of the PM that's being done. Test 11/11 and then 2025. So that's what I would use for the patient ID. Last name I would do like PM. I'm doing a patient here. So again, PM 2025. PM. Click exit here. All right, you can see here the name. I typed too many P's, but PM. You see the patient ID there. depth of penetration test, the first test that would come in here, transducer on here. I wanted to create so I'd increase my depth up here to the deepest distance that I could get. I would change my focal zones. We'll get here. Depth of penetration here. All right. I'd freeze this image. All right, here. Go to measure. Select the distance here, and then I would save this image. Once I have the depth of penetration here, this one was at, go over it again here. So I have me at length. Measure. You can see my distance, the depth here is like 7.86 centimeters on there, almost 8 centimeters on there. Again, like I'd say, I'd save the image, and then I would record that information on our PM report form that we have for each transducer. Our particular PM report form has a serial number. We record the serial number. We record what exam that we were in this particular. I'm sorry? From the top, from the distance of the top there. Sorry, let's go back. All right. The penetration. Freeze here. So when it's measuring from this arrow up here at the top. You see? And it's creating the depth.
I'm just used to seeing a line that comes down.
Yeah. With this particular one, because it's doing depth, it doesn't. So if you did more than one measurement, here, that's a typical line that you're looking for, correct? Yeah. That's just a distance measurement. Again, save that. So that's how you would complete the depth of penetration test for each transducer. Now, one thing that's in order to be able to effectively identify over time whether or not the transducer is degrading, okay, you want to make sure that you're always in the same exam. So this particular one, you could be under small parts. You could use whatever preset that you want to use. Small parts. Typically for the 12 linear, I would use a vascular preset and carotid when I did that. But anytime that I would go back and redo this test, I would make sure that I'm under the same preset as well. So in our service management software, we have a form, and this form, like I said, has serial number, has our depth of penetration test. Under the depth of penetration test, it asks us for what preset that we were in. So we would have to write down, hey, we were in this preset. This one you can find under exams, vascular, carotid, so that when you go to redo the test or going back to look at whether or not this has degradation over time, you can see that, hey, they were in the same preset or we were in the same preset. Everything looked good with this transducer. When we did the depth of penetration measurement this time, it was at 8 centimeters. And the next time that we went and did it and looked at it, it had decreased from 8 centimeters to 3 centimeters. All right, that would be a degradation that you would see. So next time we come in and do this test, say we can only see like 4 centimeters depth on this transducer, that would indicate the transducer is going bad over time. We typically do our PMs on every 6-month intervals. So if we saw that within the 6-month interval, we would say that it's having issues. Either the system's having issues or the probe's having issues. That's the depth of penetration test. Functional test. Let's see, go over here real quick. See what I got here. So that's it, the precision test. All right, let's go back here. Back over here. So, other thing I would check in transducers, we talked about select probes, presets. We went over checking an air scan. I'll show you an example of an air scan on this particular system. Back here. Oh, wait for that one to go over there. Go back to 2. So when we're checking the air scan, you're looking for good array and uniform range. You want to flex the cable to ensure there's no bad or electronic connections. And you want to move the transducer back and forth to ensure all elements are working and there are no shadows in the image. So if we go back to, I think it was 2, right? Yep, back to 2 here. One of the things when you're checking elements at the top, all right, if you scroll back and forth here lightly, sometimes you can see a dropout in the image. And the dropout you would see would be like right up here at the top here. If you saw any shadows in the image here, and typically you won't see it. Sometimes you won't see it when you just go on there right away. All right, you'd have to scroll across left and right to make sure that you don't see any dropout in a particular transducer. If you flex the cable, sometimes you get dropout there. All right, so how that one's going. So remember that. Let's go back here. All right. So we selected the probe, went over the air scan, checked elements, verified weak elements, depth of penetration. We selected presets for the transducers. We adjusted the depth and focus to the max depth. We measured the depth with the electronic calipers. The distance should remain the consistency over the lifetime of the probe. That's the depth of penetration test. The next test is the functional resolution test. This is the functional resolution test, what it's going to look like when we put it on the system here. We're going to use phantom image and anechoic target structures, which is these guys over here on the right here. We're going to view the size and shape of the targets. Typically, they're 2, 4, and 8 millimeters in distance here. You can measure the targets using the electronic calipers, adjust the focal zones to match the depth of the smallest target, examine the image, measure the depth of the smallest visible target. The distance should remain the same over the lifetime of the probe. So in this particular test, you can see they're hitting these small 2 millimeter targets. They increase their depth to the smallest one that they could see. And then they measured the distance. See here the depth. They measured the distance from the top here to the bottom here. And this is just a functional resolution of the transducer here. So we'll go over here. Same thing. You want to be in. You want to make sure that you have the same preset set. Typically, if you're doing one transducer, you're still in the same preset. You don't have to go back and change anything. So again, I'll go back here. Again, here just to show we're in a vascular preset. We're under a carotid exam still. All right. Functional resolution. All right. Typically increase your gain so you can see. All right. It's a little easier here. Your depth. All right. Let's see here. All right. You can see, even though I'm going deeper in depth here, I'm not getting any more visibility from these anechoic structures. All right. So once I got this image here, I typically, oh, wrong button. What did I hit here? Let's just go back to again, go to the smallest anechoic structures here. All right, same thing that they did on the functional resolution. So I'm going to take a depth measurement from here down to the smallest 2 millimeter anechoic structure here. And can't really see it on that screen here, but I can see it a little bit better on the ultrasound image here. So we'll just cook this one here. My depth is 4 centimeters. And so from this one, I would save this image. And then I would record it in our system management software for a particular probe. Again, same type of thing. For functional resolution, before we were just going to the depth of penetration just to see how deep the transducer goes. This is actual functional resolution or usable resolution. You can call it either way, but this would be the resolution that they could actually use to see images on particular here. So you can see it. This is carotid. And the functional portion of it, I wouldn't be able to see anything deeper than that would be usable below that 4 centimeter mark. All right, again, record it. If you saw any change or degradation over time, with this being a linear transducer, 12 linear, higher frequency, less depth of penetration here. If I started to see less, maybe 3 centimeters or 2 centimeters here in this area, then I would say that this transducer is probably going bad, and there's probably could be an issue with it in the future, or there is a issue with it at that particular point in time. All right, where are we at next? Where? This guy. So we're going to functional resolution test. Next test is a geometric accuracy test and measurement accuracy. For this particular test, we're going to hit vertical and horizontal measurements using the electronic calipers that we've been using. We're going to measure the wire pins or dots horizontally and vertically. We're going to save and print this image. Verify that the vertical target distance is within 1.5 or 1.55 millimeters, whichever is greater, and the horizontal measurement distance is within 2% or 2 millimeters. So each one of these wire dots here, all right, we're going to go between, we're going to do a horizontal, I'm going to do vertical, and then horizontal measurements of these wire dots here, and verify that they're within that 1.55 millimeter or 2 millimeter range here. Again, we're using the 12 linear transducer, so we would stay on that same preset. Oh, sorry. Hold on. Gotta go one more. Again, save here, freeze image. Now I don't have to do anything with the presets because I'm still in that same preset here. Measure. All right. Distance here. Measure again. And then I would save the image. I can see all under the clipboard here, all of these images are saved under here. So if, for accreditation purposes, for your department, if they wanted those images afterwards, we'll save them. You can save them to a USB stick, or you can send them to, you could transfer them to the DICOM workstation, let them know, and then they can, save them or print them up how they feel free for their accreditation purposes. Depth of penetration test. Accuracy test. What's that? So typically, right now it's just saved like it was on a study. But when we go to end the study, right, we could either send them to the DICOM workstation for the, where they would typically send their studies, or you can send them and save them to a USB device to give to the department in the future, so they can use them for their, accreditation purposes. All right. So back over here. All right, so we went over the geometric accuracy test, beam profile test. This is a test, it's on here and it's part of, I think it's one of the ACR accreditation tests they ask for, but this particular one I don't use that often, because really it just follows the beam path, but we'll go through and show you guys how to do it. This one, measure the width of the dots or the wire pins. You use 5 different measurements. The resolution should improve with the depth until the beam comes into focus and decrease as the beam spreads out. And then we'd save and print this image. So same thing, you would want to be in the current, still want to be in the same preset that you were in. Okay. Just to confirm, we're under vascular and the carotid preset. So this being a 12 megahertz probe, the beam form is going to come into closer to the top of the image. So you go here, we would measure. All right. I don't think we have enough to measure 5 dots here, but you'd measure each dot. Let's click that out. And what you should see on this particular one, we took 4 measurements. We'll do one more. And what you should see is from 1 to 4, you should see it start wider, right, and come in as the beam comes through. Right here, you should see like, you should see it start wide and then come into play more, and then again widen back out as the beam comes through. Is what they're looking for there. And you can see that all the measurements are they're so small and so tiny. This is the reason why I really don't use this particular one a lot, and it doesn't really tell you a whole lot for the quality of the transducer here. But it is one of the tests that is on for ACR accreditations that they ask for. So that's one of the ones that we put on there. Next test we have is axial and lateral resolution test. For the axial and lateral resolutions, we're going to hit this axial and lateral dots, wire dots right here on the left here. They're going to take a measurement between the 2 of the smallest ones that you could see distance between. You're going to image the axial and lateral dots using electronic calipers to measure the distance between 2 visible dots or wires. Save and print the image. This distance should remain consistent over the lifetime of the probe. I don't know if I got the depth here. I'll check it to do this particular one. I do. All right. All right, so for this one, we've hit the axial and lateral dots right here on the left-hand side there. We would measure. I can see a little better on the system than I can see up there, but I would measure. Typically, you would go with the smaller ones. It's not that important which ones that you pick. All right, here and here. All right, so I did this measurement between this 2 points, as long as you have an idea of which points you're measuring in the future. So typically, these are the ones that I'll stay in. And the reason I picked the 2 smallest ones is because I'm always knowing Anytime I go back to redo this test, those are the smallest ones that I always choose from, the ones that I can see with the smallest distance. You can see the length here is 0.24 centimeters. If you saw any change or any degradation in this the next time you went and did this test, would indicate there could be an issue with the transducer. I've never seen this test be off, but it's one of the tests that they asked us to do, so we go through and do it. The final test, well, I think this is the final test, or one of the final tests here, is the grayscale contrast test. Image the grayscale target structures and note which targets can be distinguished from the background speckle. All shades of gray should be clearly visible, circular in shape and varying degree of brightness, ranging from low to high levels of contrast. I don't know if I can get that depth of image. Let's see. Okay, let's go here. Now increase my depth. Go through it. All right, and I'll show you what the penetration looks like. So here, anechoic structures. Over here on the left here, you can see the grayscale right here. You can see, I can see there's 4 different grayscale measurements here. You can see that they're circular in depth. And as long as you can see all of them, pretty good. Sometimes you may have to rotate or move the transducer left and right to get a good visual, but typically, again, I would freeze this image, save it. It's basically showing that I looked at those grayscale and anechoic structures. All right, the final test that we have on here, I think it's a grayscale, or sorry, it's a cable noise test. All right, here. For a cable noise test, we want to ensure that the lens is clean and dry. You're going to enable continuous wave or color mode on the system. You're going to adjust the volume and the color gain to an acceptable level. You use the trackball to measure continuous wave cursor throughout the image, looking for noise or spikes. Flex the cable at the strain relief, looking for unacceptable noise. And see if and check the cable to make sure it doesn't have any rollover damage, flex or stress in the damaged areas. Basically, we're talking about the cable. So first thing, one of the things I would do when I come to the cable is I'd run my fingers or hands through it, see if there's any flat spots, if it's been run over by a tire or a wheel by the ultrasound system. If there is, then I would check that area. I'll show you what it looks like on the system here. So in this particular system, again, we're on the same exam, carotid here. All right, I would go into the color mode. All right, bring up the color box. All right, and if there was a flat area on the transducer where it had been run over or there was nicks or damage in the cable, I would go to that area and I'd give it a flex. All right, check to see if I see any spikes or noises within this color box right here. Sometimes you can increase the gain of that color. I'll show you what it looks like when it's all the way up. That's me. All right, so this is color at 100%, right? Just full blotted out color. All right, so I would bring that color box up to that, bring it back to an acceptable area just below where you can barely see, and then I'd give it a flex, right? If there was any noise in the cable or would have any issues, you would see color spikes like that. All right, something that looked like that or having an issue, probably even slightly smaller. But if there was an issue with the cable, that's one of the things that you would see. So I'd check it in color, and then I'd also check it in Doppler. This is pulse Doppler, so you probably won't see it as much. But come here as well. Check it. If I saw any spikes, color spikes that look like that in that area, that would indicate some defect in the cable or defect in the transducer. This particular one, I don't see any color noise, obviously, with it. Good. So I would do that in both. Same two tests for color and pulse wave or continuous wave. And then on some transducers, I would take this cursor up here, right? We call this a sample volume, and I would scroll through the whole image of the transducer as well to see if there's any other issues. And sometimes when you scroll through, right, you can start to see some noise and some issues. Now, sometimes when people do this, they're like it's dropping out or the transducer's dropping out on me. Well, you can see, let me increase the gain here. All right, when I go to move this transducer or move the sample volume, right, I see these little dropouts here. All right, it's because the sample is taking another sample from a different spot. Right, sometimes I have had people call in and say, oh, my system has problems because I've got noise in it or something's going on, when really there's just an issue with the trackball. And it's some of them are just having issues, and they're kind of moving every now and again. So which is a common problem that I see on GE systems a lot. A lot of technicians have gel and whatnot on their hands, and they're always moving the trackball. So just a heads up there, that it may not be something wrong with the transducer, but it could be something wrong with the trackball. Let's go back here, freeze. We will update that image. All right, again, we were talking about color noise. I don't see any noise in this particular transducer. You scroll through it. Some of the Philips transducers, like the X51, the X82Ts, when you scroll through here, it'll start to get loud or noisy in some of the spots there. So that could, typically that's an issue with the cabling inside the transducer, and is indicating that you have a defective either X51 or X51C or X82T transducer. Here, plug this one in. So I'm going to also show you an example of an air scan. It's one of the first things we did on a transducer that is defective. All right, so this curved linear transducer on the Philips C51. We can go through here, look on it, do some of the same tests that we were looking at before. Depth of penetration. All right, since this is curved linear transducer, we can go with more depth here. Where's our measure? All right, if it doesn't give me depth, I can go here and then here. But at first glance, this transducer would look like it's okay, right? To me, I would do a depth of penetration, 15.8 centimeters. Everything looks good to this point. I would continue on with my testing. Let's go back here to freeze. I did an air scan here at the beginning. You can see everything looks good, but when I go to do a cable noise test, all right, I can see some dropout in it. Let's see if we can get any more. You see it up there? You see that right there? Y'all see that? All right, so you do a cable noise test and you can see some dropout in there. Now everything looks good with the transducer, but that's one of the reasons why we typically make sure that we're flexing on there, because there is dropout in this particular one. I don't know if you can see it. Let me crank the gain in this area. It'll let me show it's a little too high there, but you can see when I wiggle the cable, I'm getting cable noise there. All right, this is an example of things that you would see when you're doing a QA, quality assurance testing on transducers here. So we can check the color box too. I don't know if it'll spike or not. Yep, there it is. You see a spike? All right. So indicates, sorry, a defective transducer. And one of the reasons why, we want to go through and do these quality assurance tests on each individual transducer, it can take some time. A typical PM per ultrasound system takes me about an hour if there's like 8 or 9 probes for the system. Obviously, it's quicker if there's just one, but and depending on whether or not it's a portable system or a larger system, right? These guys are quickly easy to clean out and make sure that the fans and everything's clean with them. The other systems are not. One of the things I do, I think that's everything under quality assurance for tests. Any questions on quality assurance for transducers?